Thousands of years before the modern metal key, ancient lockmakers developed a mechanism built from wood. A horizontal bolt secured the door. Small pins dropped into openings in that bolt and prevented it from moving. To unlock the door, a large toothed key was inserted beneath the pins and lifted them into the correct position. Only then could the bolt slide. The materials were simple, but the principle was revolutionary. The lock did not recognize a person's face, name, or authority. It recognized a physical pattern. That same basic idea, several internal components aligning correctly before the mechanism can move, survives inside many locks today. Over the centuries, wood was replaced by iron, brass, and steel. Keys became smaller. Internal obstacles became more complicated. Precision engineering created locks containing springs, levers, wafers, and rotating cylinders. Mass production eventually placed them on ordinary homes, offices, cabinets, and apartment doors. Electronic access later moved permission away from the metal key and into cards, codes, fingerprints, and software. But every system continued performing the same basic task, keeping almost everyone outside while allowing a selected person to enter. This is the history of how a wooden bolt became one of the most important mechanical foundations of privacy. If the hidden history behind ordinary objects fascinates you, like this video and subscribe, because before locks could protect privacy, people first had to find a way to secure a space after walking away from it. Citations are included for historical verification and can be removed before recording. Before a door could recognize a key, security depended largely on strength, concealment, and human presence. The simplest method was a heavy wooden bar placed across the inside of a door. Once lowered into brackets, the bar prevented the door from swinging inward. This could be effective while people remained inside, but it created an obvious limitation. A person leaving the building could not easily secure the bar from the outside and later return. Other methods protected property without truly locking it. Ropes could be tied around containers. Knots could make interference more difficult. Clay or wax seals could reveal that a chest, storeroom, or document had been opened. Hidden rooms and concealed entrances could keep valuables away from casual discovery. But these methods depended on secrecy or evidence. They might reveal that someone had entered. They could not always stop the entry itself. The most reliable security system was therefore another human being. A guard could watch a doorway, question visitors, and decide who should pass. Servants could protect household entrances. Soldiers could control gates. Merchants could sleep beside valuable goods. But a guard needed food, rest, and payment. A guard could become distracted, intimidated, bribed, or disloyal. Once the person responsible for security walked away, the protection weakened immediately. This was the problem the lock eventually solved. The great breakthrough was not merely attaching something to a door. People had used bars, latches, and bolts for centuries. The breakthrough was creating a mechanism that could be secured and later released from outside by an authorized person carrying a portable object. That object became the key. A key allowed a person to leave a protected space without surrendering control over it. The owner did not need to remain beside the entrance. A servant did not need to stand permanently on guard. The door could continue enforcing the boundary after everyone had walked away. The earliest locks could not identify people in the modern sense. They could not recognize a face, name, or legal right. They recognized a shape. Anyone possessing the correct shape could operate the mechanism. This introduced the central contradiction that still defines locking systems today. The lock could distinguish between the correct key and the wrong key. It could not distinguish between the rightful owner and a thief holding the correct key. Even so, this was an extraordinary change. Privacy no longer depended entirely on trust, physical presence, or social rules. A mechanism could help enforce it, and the earliest important version of that mechanism was made almost completely from wood. Wooden lock parts recovered from Egypt and Nubia show that early locking systems could use bolts, movable tumblers, and keys with projecting teeth. Surviving museum objects include wooden lock blocks containing rectangular openings for tumblers, wooden bolts with recesses designed to receive those tumblers, and individual carved components that once moved inside the mechanism. These objects document a locking tradition based on internal alignment rather than a simple external latch. The mechanism worked through gravity. A horizontal wooden bolt slid between the door and its frame. When the door was secured, small wooden pins or tumblers dropped into openings in the bolt. As long as those pins remained inside the openings, the bolt could not slide. The door stayed closed. To unlock it, the user inserted a large wooden key through an opening beneath the bolt. Teeth projecting from the key lifted the internal pins. When every pin rose high enough to clear the bolt, the user could slide it sideways and open the door. The lock performed a simple form of mechanical recognition. The correct key placed several internal pieces into the required positions at the same time. A key with missing teeth, incorrectly spaced projections, or the wrong height would fail to lift the tumblers properly. The materials were basic. The principle was not. A barrier was no longer secured only by its weight. Hidden components inside the lock had to be aligned before the barrier could move. That concept remains central to many later locks. Modern pin tumbler cylinders use metal pins, springs, a rotating plug, and a much smaller key. Their construction is far more precise, but they preserve the broader idea that several internal parts must reach the correct alignment before movement becomes possible. The ancient system also created the first major relationship between a lock and its key pattern. The lock could be modified by changing the number, spacing, or position of its tumblers. The key then had to match those internal conditions. More possible arrangements meant fewer unrelated keys would work. But wooden locks had obvious limitations. They were physically large. The keys could be long and awkward to carry. Exposed wooden parts could swell, crack, wear, or be damaged. A strong attacker might break the mechanism rather than solve it. The lock protected the door only as long as the surrounding material remained stronger than the force used against it. Metalworking would make keys smaller and mechanisms more durable. It would also allow locks to protect more than the main entrance of a building. Greek and Roman craftspeople developed a wide variety of metal keys and locking mechanisms. Surviving Roman examples include iron door keys, bronze slide keys, padlock keys, and small keys attached to rings. Some were designed for simple tumbler locks. Others contained elaborate cuts intended to pass fixed obstacles inside the mechanism. One Romano-British iron key held by the British Museum has an unusually complex bit shaped to pass 11 wards. Other Roman keys survive as small L-shaped tools with several projecting teeth, while some were attached to rings that could be worn on a finger or carried from a belt. The key was becoming portable authority. A person no longer needed to carry a large wooden tool associated with one heavy lock. Metal allowed keys to become thinner, stronger, and more suitable for everyday use. Some Roman locks continued using tumbler principles. The key lifted or moved internal parts so that a bolt could slide. Others relied on wards. A ward was a fixed obstruction placed inside the lock. The correct key contained cuts that allowed it to move around those obstacles and reach the locking mechanism. An incorrect key struck the wards and could not turn far enough to move the bolt. This appeared to create a sophisticated barrier. The key had to possess the correct shape, and the lock's important features remained hidden inside the door or container. But warded locks contained an important weakness. The key did not necessarily have to fill every empty space inside the mechanism. It only needed to avoid the obstacles and reach the part that operated the bolt. A simplified key with much of its metal removed could sometimes pass around several different ward patterns. This later became associated with the skeleton key, a key reduced to the minimum shape needed to bypass internal obstructions. Roman locks also expanded the scale of personal security. A lock no longer belonged only to a building gate. It could protect a box, cabinet, chest, storeroom, or personal collection of valuables. Smaller locks created smaller private boundaries inside larger shared spaces. A household might have one main door, but separate locks could control access to food, money, jewelry, documents, or tools. This was an important development in the history of privacy. Privacy could now exist at several levels. A city wall protected the community. A house door protected the family. A locked room protected selected members of that family. A locked chest protected the property of one individual. The key showed who had permission to cross each boundary. It also became a symbol of authority. The person carrying the key was often the person trusted with control over the space behind it. As European societies moved into the medieval period, keys and locks became increasingly decorative. Their appearance became more impressive. Their actual security did not always improve at the same speed. Medieval and early modern locksmiths transformed functional hardware into elaborate metalwork. Locks were fitted to doors, strongboxes, church chests, cabinets, and containers used to protect money, documents, and valuable objects. Their external plates could include architectural patterns, pierced iron designs, floral forms, and miniature figures. The Metropolitan Museum of Art notes that Gothic locks and keys were often decorated to a very high standard. Some compound locks concealed parts of their mechanisms and required 2 or 3 keys used in sequence. The increasing use of locks during the later medieval period has been associated with urbanization, material wealth, and a stronger emphasis on private ownership. The lock was becoming both a practical device and a public statement. A large iron plate fixed to a chest suggested that the contents were valuable. An oversized key could communicate responsibility and office. Keys were carried by household officials, custodians, religious authorities, and chamberlains. In some contexts, ceremonial keys represented the right to enter or supervise important spaces, even when their practical function was limited. But elaborate appearance could create false confidence. Many medieval and early modern locks still depended on wards. A locksmith could arrange internal obstacles into complex patterns, then cut a key capable of passing around them. From the owner's perspective, the key looked unique. From the attacker's perspective, the important question was whether the mechanism could be reached without reproducing the full shape. A lock might also be defeated without manipulating it at all. An attacker could damage the door, split the chest, remove hinges, or cut through the surrounding material. A massive lock plate attached to weak timber protected only the strongest-looking part of a vulnerable system. This revealed a principle that remains true of modern security. A lock does not protect a space independently. It protects one point in a larger boundary. That boundary also includes the door, frame, hinges, walls, windows, key control practices, and people using the system. Locksmithing gradually became a recognized specialist craft. Producing springs, bolts, wards, and carefully shaped keys required experience and precision. But before industrial machine tools, many parts were still filed and fitted by hand. 2 locks built to the same general design might behave differently because each mechanism contains small variations created during manufacture. This made locks expensive and difficult to reproduce consistently. It also limited how precisely internal parts could be arranged. By the 18th century, a new generation of British lockmakers began approaching security as a mechanical engineering problem. They would use tighter tolerances, specialized components, and purpose-built machinery to create locks that were harder to inspect and manipulate. The most famous of these designs was associated with Joseph Bramah. Joseph Bramah was an English inventor and engineer working during the early Industrial Revolution. His lock, patented in the late 18th century, abandoned the familiar large bit key used by many warded mechanisms. Instead, it used a compact cylindrical key and a set of internal sliders arranged around the keyway. When the correct key was inserted, carefully cut slots on the key pushed the sliders to different depths. Only when every slider reached its required position could the mechanism rotate and release the lock. The principle greatly increased the number of possible internal arrangements. It also made the working parts difficult to observe through the keyhole. The lock's security depended on precision. A slider moved too far or not far enough would continue blocking the mechanism. The key had to control several components simultaneously, and each component had to be manufactured accurately. Science Museum Group collections preserve Bramah locks, working models, and the famous challenge padlock later associated with the Great Lock controversy. This precision created a manufacturing problem. Traditional filing and hand-fitting could produce individual locks, but consistent production demanded better tools. Bramah's workshops developed specialist equipment for shaping parts, cutting lock components, and producing springs. The history of the Bramah lock, therefore, belongs partly to the history of machine tools. The lock did not simply benefit from precision engineering. Its demands helped encourage precision engineering. Bramah became confident enough in the mechanism to issue a public challenge. A special lock was displayed with an offer of a reward to anyone who could open it without the correct key. The surviving challenge board dates to 1801. For decades, the challenge strengthened the lock's reputation. It suggested that Bramah had created something beyond ordinary locksmithing, a mechanism so precisely constructed and internally complex that manipulation was effectively impossible. The lock became a symbol of industrial confidence. Security no longer depended only on thick iron. It could depend on the exact relationship between tiny internal parts. This mattered in a society containing growing banks, commercial offices, manufacturers, and urban households. More people stored money, contracts, records, and valuable goods away from direct supervision. A stronger lock could protect property, while its owner conducted business elsewhere. The Bramah design did not make privacy absolute. It made unauthorized access more technically demanding. That difference is important. Every lock imposes a cost on an attacker. The cost may be time, knowledge, tools, noise, or physical force. A successful lock makes that cost high enough that the attacker gives up, is discovered, or chooses an easier target. Bramah attempted to raise the cost through precision and complexity. The Chubb brothers would introduce another idea. A lock should not only resist interference, it should reveal that interference had taken place. In 1818, Jeremiah and Charles Chubb patented what became known as the detector lock. Science Museum Group records identify the brothers with the 1818 patent and preserve working models and surviving examples of their lever mechanisms. The Chubb design used a series of levers. When the correct key turned, its shaped edge lifted each lever to a precise height. Once the gates and the levers aligned correctly, a stump connected to the bolt could pass through them. The bolt was then free to move. If a person attempted to manipulate the lock and raised one of the levers too high, the detector mechanism could be triggered. The lock entered a secure state. Normal operation was prevented, and the condition indicated that someone had interfered with the mechanism. The authorized key holder could then use the proper procedure to reset and open it. This introduced an important security distinction. Prevention asks, can the attacker be stopped? Detection asks, can the system reveal that an attack was attempted? A lock may resist manipulation for several minutes and still eventually be opened. But if the attempt triggers a warning, the owner gains valuable information. Modern security systems use the same broader principle. Alarms record forced entry. Computer systems log failed access attempts. Access control systems preserve records showing which credential was rejected and when. Chubb's detector lock applied that logic mechanically. The design became associated with high security applications, including commercial property, government institutions, safes, and secure storage. Lever locks also became important on ordinary doors in Britain and other countries. Their internal arrangements differed from Yale-style pin cylinders, but they followed the same fundamental requirement. Several components had to reach the correct alignment before the bolt could move. The Chubb lock's reputation grew as the company expanded. Its name became closely connected with British lock and safe manufacturing. By the middle of the 19th century, British manufacturers promoted Bramah and Chubb mechanisms as evidence of the nation's engineering skill. Then the Great Exhibition of 1851 brought industrial products from many countries into the same public space. It also brought Alfred Charles Hobbs, and Hobbs arrived prepared to challenge the difference between a lock's reputation and its actual resistance. The Great Exhibition of 1851 celebrated manufacturing, machinery, and industrial achievement. Britain presented itself as the center of modern engineering. Locks were part of that display. They represented precision, property, banking, and the ability of industry to protect the wealth it created. Alfred Charles Hobbs was an American locksmith who traveled to London in connection with American-made locks. He publicly challenged respected British security mechanisms and demonstrated methods of opening locks regarded as exceptionally secure. Science Museum Group records identify Hobbs as the first person to pick Bramah's famous challenge lock. The surviving 1801 padlock remains associated with the lock controversy of 1851. The Bramah challenge was not defeated quickly. Hobbs worked over an extended period under controlled conditions. That fact is important. His achievement did not mean that an ordinary criminal could silently open the lock in seconds. It demonstrated that a knowledgeable and determined attacker could analyze the mechanism, create specialized tools, and eventually overcome its defenses. The controversy damaged the idea that a lock could be trusted simply because its construction was secret or its maker had declared it unbeatable. Hobbs exposed a permanent truth about security claims. A mechanism should not be considered secure merely because most people do not understand it. The relevant question is, what happens when a skilled attacker does understand it? Public demonstrations of lockpicking forced manufacturers to reassess their designs. Lockmakers studied the tools and methods used against their products. They modified internal components, added false gates, and improved tolerances. Attackers then studied the changes. The history of locks became a continuing arms race. This was not evidence that locks had failed as an invention. A lock does not need to be mathematically impossible to defeat. It needs to delay, discourage, expose, or complicate unauthorized access. Hobbs's achievement therefore strengthened the field in the long term. It replaced confidence, based on reputation, with a more demanding standard, based on testing. The Great Lock controversy also provides a useful warning for every later technology. Manufacturers would eventually describe electronic locks, digital credentials, and biometric systems as more secure than physical keys. But every system still had assumptions. Every system still had failure points. And every system still needed to survive contact with someone actively searching for them. While Britain debated precision locks, American inventors were developing mechanisms designed for widespread everyday use. One of them returned to the ancient principle of movable pins. He made the mechanism compact enough to fit inside a small metal cylinder. Linus Yale Jr. belonged to an American family already involved in lockmaking. During the 1850s and 1860s, he produced multiple designs for drawers, safes, banks, and doors. His patents reveal repeated attempts to make locks smaller, more precise, and harder to analyze through the keyway. His most influential work was the compact cylinder pin tumbler lock. The cylinder contains a rotating central plug surrounded by an outer housing. Small pin pairs sit inside vertical chambers, crossing the boundary between those two parts. Springs push the pins downward. When no key is inserted, one or more pins cross the line between the plug and housing. This prevents the plug from rotating. That boundary is known as the shear line. The key contains a series of cuts at different depths. When the correct key enters, each cut raises its pin pair to a specific height. The dividing point between the upper and lower pin aligns precisely with the shear line. Once every pin pair reaches that alignment, nothing crosses the boundary. The plug can rotate. Its movement operates the lock's cam, latch, or bolt. An incorrect key may lift some pins correctly, but leave others too high or too low. Even one misaligned pin can block rotation. The principle resembles older pin and bolt mechanisms, but Yale transformed it through metal springs, precision components, a rotating plug, and a small flat key. His 1865 patent describes improvements chiefly applicable to pin locks and includes a cylinder, tumbler case, springs, and key-operated components. Yale's company history identifies the cylinder pin tumbler lock as the family's best-known design. The design offered several practical advantages. The cylinder was compact. It could be installed separately from the larger lock case operating the door bolt. Manufacturers could produce many key patterns. A small flat key was easier to carry and duplicate than many earlier large bit keys. The cylinder could also be replaced or reconfigured without replacing every part of the door hardware. This helped make the lock suitable for mass production. The mechanism did not remain confined to banks or wealthy households. It could be placed on shops, offices, apartment doors, cabinets, and ordinary homes. The cylinder lock brought precision access control into daily life. Its appearance became so familiar that many people stopped seeing it as complex machinery. They inserted a key, turned it, and expected the door to open. Inside, several spring-loaded components performed a precise alignment inherited from one of the oldest ideas in lock history. But widespread adoption created a new problem. When one lock protected one chest, one key could be carefully controlled. When a building contained hundreds of locks, privacy depended on managing hundreds of permissions. Industrial manufacturing reduced the cost of locks and made their components more consistent. Parts could be produced to standard dimensions. Locks could be sold in large numbers. Replacement hardware became easier to obtain. Security moved from specialist strong rooms into ordinary buildings. Homes gained locks on exterior doors. Bedrooms could be locked separately. Offices protected files and supplies. Shops secured storerooms. Schools, hospitals, factories, and hotels divided their buildings into zones of permission. This changed the structure of privacy. An entire household no longer needed to share one protected boundary. One person could secure a room inside the home. A worker could lock a desk inside an office. A hotel guest could control one room inside a building filled with strangers. A tenant could possess a key that opened an apartment, but not the landlord's office or another tenant's home. Mass lock use required systems rather than isolated mechanisms. Master key arrangements allowed one key to open several locks, while individual keys opened only assigned doors. A building manager might carry a master key. Tenants or employees received more limited keys. The lock could therefore recognize levels of authority through mechanical design. But every additional key created a management problem. Keys were lost. Copies were made. Employees left jobs without returning them. Former tenants retained duplicates. A key could continue granting access long after the owner believed permission had ended. Changing this permission might require replacing or rekeying the lock. This revealed a weakness in physical credentials. The lock recognized the key. It did not know whether the key had been canceled. Once a copy existed, the mechanism could not distinguish it from the original. Hotels experienced this problem on a large scale. Hundreds of guests used temporary rooms, and keys constantly changed hands. Offices and institutions had similar concerns. Administrators needed to know who could enter each area and how quickly that permission could be withdrawn. The mechanical key made privacy portable. Mass production made it widespread. But large organizations needed access to become more flexible. They wanted credentials that could expire. They wanted permissions that could be changed. They wanted systems capable of recording when a protected door had been used. Before digital electronics, lockmakers first explored mechanisms based on information and time. A physical key represents something a person possesses. Combination locks introduced another kind of credential: information. Instead of inserting a shaped object, the authorized user entered a sequence of numbers or positions. Internal wheels, discs, or levers moved into alignment. When the correct combination was entered, gates inside the mechanism lined up and allowed the bolt to release. The lock no longer depended entirely on an object that could be physically copied. But information created different weaknesses. A combination could be observed. It could be written down. It could be shared. it could be forgotten. The lock could not determine whether the person entering the numbers had learned them legitimately. Banking created even more demanding security problems. A vault might need to remain closed, even when an employee possessed the correct combination. This led to the development of time locks. Clockwork mechanisms prevented a safe or vault from opening until a preset period had passed. The Smithsonian preserves Yale Lock Manufacturing Company patent models from 1877 associated with time lock mechanisms. A time lock added a condition beyond identity or possession. Access depended on the correct moment. Even an authorized employee could not open the vault outside the permitted period. This protected institutions against coercion. A robber could threaten a bank employee, but the employee could not provide access before the timer allowed it. Combinations and time locks expanded the logic of permission. A key asked, "Do you possess the correct object?" A combination asked, "Do you know the correct information?" A time lock asked, "Is access permitted now?" Modern identity systems organize authentication in a similar way. NIST describes common authentication factors as something a person knows, something they possess, and something they are, such as a biometric characteristic. The language is modern. The categories developed from much older security ideas. A key was something carried. A combination was something remembered. A signature, face or fingerprint connected permission to the person. During the 20th century, electrical systems began combining these factors with central administration. The lock would no longer make every access decision entirely through metal parts inside the door. Electrical locking systems changed the relationship between the door and the credential. An electric strike could release a locked entrance after receiving a signal from a nearby button, security desk, or distant apartment. Later systems used keypads, magnetic stripe cards, proximity badges, and centrally managed access credentials. A reader at the door collected information. A controller compared it with stored permissions. The system then granted or denied access. This separated the visible lock from the decision-making process. The mechanism holding the door closed might remain simple. The intelligence controlling it could exist elsewhere in the building or on a central server. Electronic access offered major administrative advantages. A lost card could be canceled without replacing the lock. A new employee could receive permission for selected areas. A contractor's access could expire automatically. Different doors could operate on different schedules. Entry attempts could be recorded. NIST's physical access standards describe systems involving cards, readers, PIN devices, biometric capture equipment, credential management, and back-end access control components. The reader communicates credential information to systems that decide whether to grant or deny entry. This changed what a lock could know. A mechanical cylinder knew only whether its pins had aligned. An electronic system could evaluate who is requesting access, which door are they using, what time is it, has the credential expired, has permission been revoked, should the attempt be logged. Large hotels adopted centrally administered electronic room locks. Modern hotel access designs can encode credentials for specific doors, while back-end systems manage permissions. But electronic systems introduced new dependencies. A physical key could continue working during a power failure. An electronic reader might require electricity, wiring, batteries, or backup power. A mechanical lock could fail because of wear, corrosion, or damage. An electronic lock could fail because of software, configuration, network problems, or corrupted credential data. The security boundary had expanded. It no longer included only the door, frame, cylinder, and key. It included databases, card issuers, administrators, cables, readers, and computer systems. The advantage was control. The risk was complexity. Every new component offered a useful function. Every component also became another possible failure point. The smart lock would bring that same transformation into the ordinary home. Modern smart locks combine traditional door hardware with electronic credentials and networked controls. Some accept numeric codes. Others recognize a smartphone through Bluetooth or Wi-Fi. Some use cards, tags, or fingerprints. A user may unlock the door remotely, create a temporary code for a guest, or check whether the lock is currently secured. These systems can solve familiar problems. A homeowner does not need to hide a spare key. A cleaner or contractor can receive temporary access. A guest's code can expire after one visit. A record may show when the door was unlocked. Automatic locking can secure the door after the user leaves. But smart locks do not remove the old security trade-off. They move it. A traditional cylinder asks the owner to protect the physical key. A smart system may ask the owner to protect a phone, password, online account, wireless connection, and digital permissions. The credential may now be something the user knows, something they possess, or something they are. NIST identifies passwords and PINs as knowledge factors, devices and security tokens as possession factors, and fingerprints or faces as biometric factors. Digital credentials can be canceled more easily than metal keys. They can also fail in unfamiliar ways. A battery may lose power, a phone may be lost, an account may become inaccessible, software may contain a vulnerability, a user may accidentally share a code, a company may discontinue support for an older product, the owner may possess the door and lock, while depending on remote software to manage part of the access system. Smart locks may also create data. A mechanical key usually leaves no record of the moment it was used. An electronic system may record a time, credential, door and access result. This can improve accountability. It can also reveal patterns of movement. The history of locks has therefore moved from controlling physical entry to managing identity information. Ancient tumblers recognized the shape of a wooden key. Industrial cylinders recognized the cuts of a metal key. Electronic systems recognize credentials stored in cards and databases. Smart locks may recognize a phone, account, fingerprint, or temporary code. Each development increases flexibility. Each development changes where trust must be placed. The traditional lock asks the user to trust the metal. The smart lock asks the user to trust the metal, electronics, and software together. Neither system guarantees privacy automatically. The result still depends on how the complete boundary is designed and managed. A lock protects one point of entry. It does not protect the entire building by itself. A strong cylinder installed in a weak door may offer little real resistance. A reinforced door inside a weak frame can be forced away from its supports. Exposed hinges may be attacked. A nearby window may provide an easier route. A spare key may be discovered. A code may be shared. An authorized person may hold the door open for someone else. Security professionals therefore treat access control as a system. NIST guidance for protected facilities includes verifying access authorizations, controlling entry and exit points, maintaining access logs, and securing keys, combinations, and other access devices. The lock remains important, but it cannot compensate for every weakness surrounding it. This lesson appears throughout its history. Ancient wooden locks were limited by the strength of their wooden doors. Warded locks were limited by simplified keys and accessible bolts. Precision locks were limited by the possibility that skilled attackers could study them. Mass key systems were limited by uncontrolled duplication. Electronic systems are limited by administration, power, and data security. Smart locks are limited by both physical and digital weaknesses. The lock also cannot determine whether a boundary is morally or legally justified. It does not know whether the person outside is an intruder, tenant, police officer, family member, or rightful owner. It performs only the rule built into its mechanism. Correct key, correct code. Approved card. Recognized credential. Access granted. Everything else belongs to society, law, and human judgment. This is why the lock did not invent privacy completely. Privacy also depends on architecture, custom, legal rights, and the willingness of others to respect personal boundaries. What the lock provided was mechanical selectivity. It allowed the boundary to remain closed by default. It converted permission into physical movement. When the correct credential was presented, pins aligned, Levers lifted, wheels rotated, or an electronic signal released the bolt. Without that permission, the mechanism remained in place, from the wooden tumbler to the smart deadbolt. This has remained the lock's essential function. It turns an abstract decision, who may enter, into a physical condition at the door. The history of the lock began with a wooden bolt held in place by movable pins. The correct key lifted those pins and allowed the barrier to slide. Metalworking made keys portable. Wards and levers made mechanisms more complex. Joseph Brema turned lockmaking into precision engineering. The Chubb detector lock introduced mechanical evidence of tampering. Alfred Charles Hobbs demonstrated that reputation could not replace testing. Linus Yale Jr. placed the ancient pin alignment principle inside a compact cylinder suited to mass production. Combination and time locks separated access from the physical key. Electronic systems turned credentials into centrally managed permissions. Smart locks moved part of the mechanism into phones, software, and biometric identity. Yet the purpose of the lock has remained remarkably stable. It allows a boundary to remain closed to almost everyone, while opening for selected people. The lock did not create the human desire for privacy. It gave that desire a bolt, a key, and a mechanism capable of enforcing permission, even after the owner had walked away. If this history changed the way you see the lock on your door, like the video and subscribe for more hidden histories of the inventions that quietly built modern life.